Hi, welcome back. Hope you had a nice little break. Um, I did not. I sat here trying to upload something to YouTube. That's how it goes, right? I love technology. I love it so much. Okay, next, I want to talk about an idea or something that comes out of the fact that we can have specific anions and cations acting as acids and bases. That means that if we form a solution using ionic salts that contain these anions or cations, we'll end up having an acidic or basic solution. Okay, so that means that when we make a solution out of specific salts, we can end up with an acid base. Excuse me, acidic or basic solutions. Okay, some ions act as bases. For example, the bicarbonate ion reacts with liquid water to form carbonic acid. Okay. But it turns out that bicarbonate doesn't exist independently of a counter ion. Okay, it does not exist independently of a counter ion. For example, sodium bicarbonate. Whoa. Weird B. So, raise your hand. Who can tell me what sodium bicarbonate is? Nobody's raising their hand. What's going on? Sodium bicarbonate is just baking soda, right? The stuff you have in your cabinet, the stuff that you make bread with. Turns out if you dissolve it into solution, we have sodium, which is the positive ion, and bicarbonate, HCO3 minus, right? When you put these into solution, when you put these into solution, they form, let me turn the volume down real quick so you guys don't get blasted with my email notification sound. They form, of course, sodium and bicarbonate. Okay, so this is the salt. This doesn't affect pH. And this raises pH. Oops. Right? It raises the pH because it's acting as a base. So we can have all sorts of different solutions that we can make using salts where the salt solution actually becomes acidic or basic. Okay, so we have a general rule of thumb. Wow. In general, anions tend to form basic or neutral solutions. And cations tend to form acidic or neutral solutions. Okay, so anions, if they're going to form any sort of pH non-neutral solution, it will be basic. And cations will, of course, form acidic or neutral. Okay, let's look at some examples of common anions that we might encounter. Well, our favorite anion, chloride, right? We have chloride, we have fluoride. Let's see what else. We have NO3 minus, nitrate. We have CH3COO minus, acetate. Okay. Now these are all conjugate bases of this acid. Of course, this is acetic acid here, CH3COOH. This is nitric acid, HNO3. This is hydrofluoric acid, HF. And this is hydrochloric acid, HCl. Okay, so these are all conjugate bases of these acids, but they are also very common anions. Okay, so every anion can potentially act as a base, but not every anion does. Okay, so they can all potentially act as a base. As you can see here, you can add a proton onto the Cl minus and form HCl or HCl, etc., etc. So you can potentially use every single one of these anions as a base, but the thing is, not all of them are going to act as a base. If the anion is a conjugate, is the conjugate base of a weak acid, that means that this conjugate anion itself is a weak base. If the anion is a conjugate base of a strong acid, it will be pH neutral. Okay, so if I form, for example, chloride, right? Chloride is the conjugate base of a very strong acid, HCl. If I form a solution with chloride in it, not HCl, but with chloride in it, for example, if I dissolve sodium chloride into some water, the question is, am I going to be making the solution slightly basic by adding this chloride in? The answer is no. Since this ion is a conjugate base of a strong acid, i.e. HCl, that means that the chloride ions in solution will have a net neutral effect on the pH. So you're not going to change the pH at all by dissolving sodium chloride. However, if you have sodium acetate, right? If you dissolve sodium acetate into water, then this is the conjugate base of a weak acid. Okay, it's a conjugate base of acetic acid, which is weak, which means that it itself is a weak base. So some of that acetate in solution will actually protonate. And since it's protonating, it's pulling the proton away from the water. It's producing OH minus in solution. Therefore, the pH of the system will increase. Okay, if you have an interesting example here is fluoride. Now, HF, even though it's a very dangerous material, is actually is a weak acid. It does not completely disassociate in water. And this is because fluoride is so electronegative that it will not let go of the hydrogen. It will not let go of the proton. So in solution, some of the HF actually exists as HF in and of itself. It's non-dissociated. So it's a weak acid. And so it turns out that if you have fluoride in solution, it will act as a weak base. and it will react with H2O to form HF and OH minus. Okay, so you're going to have a little bit of increasing in the pH due to fluoride being present in the solution. Okay, if we look on a scale of strong acid going up, so we have acid strength on this axis and base strength on this axis. We have HCl, for example, way up at the top. And we have its conjugate base, Cl minus. HCl is a very strong acid, so its conjugate base is extremely weak or neutral. In this case, we can also write nitric acid here. And the conjugate base, a nitrate, is also so weak in terms of base that it's completely neutral. Let's do a different color here. And we'll put those in a little box. And these are pH neutral. Okay. Next, something like bicarbonate or carbonic acid. Okay, carbonic acid here. And then we have bicarbonate as the base. Or we can have the ammonium, NH4+, that's the acid form. And on this side, NH3. These will all form in the mid-range, will form, oops, I don't want to write that over there. These are going to be weak bases. Right, and here we have weak acids. And here we have strong acids. Okay, let's move down to some strong bases. For example, S2 minus and O2 minus. These are very strong bases, and they produce HS minus, oops, and OH minus. Okay, those are the acid forms, or the conjugate acids. So these are essentially negligible acidity. Okay, so pH neutral, essentially. And these are extremely strong bases. Okay? Now, let's find a really interesting, there is a really interesting relationship between Ka and Kb. So let's look at both of these for this reaction here. So if we have a acid, HA, reacting with water to form H3O plus and A minus, yeah? Or, so this would be Ka, or we have A minus reacting with H3O plus to form or we have A minus reacting with H2O to form the protonated acid and OH minus. Okay, this would be Kb. So those are the two acid-base reactions we can have with this HA system. Now, we can write out what Ka and Kb actually are. Ka is equal to H3O plus times A minus. So this is just the products of this first guy up here. divided by the reactants. In this case, we only have HA because water doesn't matter. And now we have KB is equal to the products, which is just HA and OH minus, divided by A minus. Again, water doesn't matter. Now, what happens if we take these two and multiply them together? What happens? We have Ka times Kb is equal to H3O plus times A minus divided by HA multiplied by HA times OH minus divided by A minus. Okay, some interesting things are happening. HA cancels, right? A minus cancels, and we are left with right? OH minus times H3O plus. This is equal to Kw. So we found a very interesting relationship here. Ka times Kb for a conjugate acid-base pair is equal to Kw. Okay, that means that if we know the Ka for an acid, we can know the Kb of the conjugate base. For example, acetate and acetic acid. We have CH3COOH. We know the Ka is equal to 1.8 times 10 to the minus 5. What if we want to know the Kb of the acetate ion? Say we make some solution of sodium acetate and we have some concentration of acetate ion in solution, and we want to know what the pH will be. We need the Kb for this, and we can calculate the Kb by using our relationship above. Ka times Kb is equal to Kw. So we know that Kb is equal to Kw divided by Ka. So really useful expression here. And this is just 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And we get 5.6 times 10 to the minus 10. And that's the Kb for the acetate ion. Now we know Kb, and thus we can find pH of the solution that contains this base. Okay, so this is a really useful expression. Ka times Kb is equal to Kw. It's almost as useful as OH minus times H plus is equal to Kw. It's actually the same expression, just kind of moved around a little bit. Okay, let's do an example with this. Let's do an example. Let's say we have a 0.100 molar sodium acetate solution. Okay, sodium acetate solution. We know that when we put sodium acetate into solution, we are going to form sodium plus and acetate, right? This has no effect on the pH. Right? It doesn't affect the pH. Actually, I guess that's an E effect. Okay, there's no effect. And of course, this is a weak base, so it's going to affect the pH. And we know that Kb is equal to Kw over Ka. We know the Ka of acetic acid by looking it up, so we can find the Kb of that conjugate base. And actually, we just calculated above. It's 1.8 times 10 to the minus 5. Wait a minute, no. Sorry, that's the Ka. The Kb is 5.6 times 10 to the minus 10. Okay, so now we have the Kb. In our solution, the reaction that's going to be important for us is the acetate ion reacting with H2O to form acetic acid. Oops. Okay, that's the important reaction. Now we just need to set up an ice table. We have our acetate here, concentration. That's our only reactant that we care about. And then the other side, our acetic acid concentration and our OH minus concentration. Okay, so initially we have 0.100 molar of acetate. Okay, this is going to completely disassociate when we put it into a solution, mostly because sodium acetate or any sodium salt are completely soluble, highly soluble in solution. We have 0 amount of acetic acid present, and we have approximately 0 amount of OH minus present in solution. We're going to represent the increase in OH minus as X, so that means that we have negative X from the acetate. We have plus X for the acetic acid, and we have plus X for the OH minus. Now, at the end, at equilibrium, this gives us 0.100 minus X for the acetate, X for the acetic acid, and X for the OH minus. We can find Kb by setting these guys, let's see, CH3COOH multiplied by OH minus divided by CH3COO minus. Okay, this is equal to X squared at equilibrium divided by 0.100 minus X. Okay, we're going to assume that X is small. And this is a great assumption because Kb is so tiny. It's times 10 to the minus 10. So we know that there's really not going to be that much OH minus in solution. That means that we can take the square root of 5.56 times 10 to the minus 10 multiplied by 0.100, and this gives us X. And we find that X is equal to 2.4 times 10 to the minus 6. Okay, 2.4 times 10 to the minus 6 versus 0.100. This is obviously less than 5%. So with our check is successful. We have less than 5%. So our assumption is good. So that means that our OH minus concentration is equal to 2.4 times 10 to the minus 6 molar. Okay, now we can calculate the H3O plus concentration because we're interested here in the pH. So H3O plus is equal to 1.00 times 10 to the minus 14 at kW divided by 2.4 times 10 to the minus 6, and we end up with 4.2 times 10 to the minus 9 molar. Okay, pH of that, whoa. What the? Hello? Guys. I'm freezing for some reason. Okay, hopefully I can stop this and come back in a second. Okay, guys, I'm back. Hopefully it's working. That was really weird. My whole computer just kind of like froze up. Anyway, I'm back, and let's finish this problem real quick. So we have this H3O plus concentration here. All we have to do is plug that into our pH formula, negative log of the H3O plus concentration. In this case, 4.2 times 10 to the minus 9 molar, and that ends up equaling 8.38. Okay, so I have two decimal places there. That's because I initially put in something with two significant figures. Okay, so the pH of our solution of sodium acetate ends up being 8.38. Okay, that's how we can use our ideas that we've come up with for acids and bases to figure out the pH, or the basicity of a solution that's made purely from sodium, a sodium salt of bicarbonate. Okay, there we are. This is like a 10-second clip. I just wanted to throw this on there so you don't have some cliffhanger until Wednesday, Don't want to leave you for, 2 days not knowing what the pH could be. Anyway, there you go. There's the pH. I hope you guys have a better day than I'm having so far. And I will see you back here on Wednesday. Take care.